Section R.2 covers some basic concepts from algebra. So let's go over those. So the first thing is a little bit of set theory, right? So a set is a collection of any objects, right? These objects could be countries, cities, years, numbers. In our case, it's going to be numbers or letters. And all the numbers in a set are called the elements. And we denote a set by listing the elements inside a pair of braces. So let's go ahead and make up a set 1, 2, 3. Very exciting, I know. The elements in this set are 1, 2, and 3. A set could also be specified by giving a description of its elements. Say I could do all countries in Asia. That would be a set. And we can define those mathematically as well. And I'll show you that in a couple slides. Friendly reminder that you can have a set containing no elements, and that's the empty set. And we denote it like this. It's just a 0 with a slash through it. You don't want to put it in this brackets. Don't put it in brackets, because that gives me the set containing just the empty set symbol. See, super warning. Let's change color. So to be a finite set means we can count the number of elements that set contains, okay? So some examples of finite sets would be A, B, C, D, E, F, G, because we can count it has 1, 2, 3, 4, 5, 6, 7 elements. For the set of 1, 2, 3, I can tell it has 3 elements. When a set contains its element, we would say that element is in the set. So we could denote that with this symbol. It's like a really stretched out E, kind of looks like the euro symbol, right? So that means element of. So here I say 2 is an element of 1, 2, 3, and B is an element of this set, A, B, C, D, E, F, G. Note, I'm separating all the elements with commas because the set FG doesn't equal the set FG if there's no comma, because then this is 1 element and these are 2 elements. Provender for thought. Some sets are infinite, right? We know infinity exists. An example of an infinite set would be something we can't count, and that could be the natural numbers. The natural numbers are also referred to as the counting numbers, and that's just how we start to count. So the natural numbers are 1, 2, 3, 4, 5, and on and on and on forever. That ... means the pattern keeps on going. The natural numbers are an example of a number family, and we actually have quite a few different number families I'd like to talk to you guys about. But first, I want to show you how I can write number families in set builder notation. So we use a variable to represent and define our set of numbers. So for example, here I say, I've got my bracket, so I have the set of numbers such that, that's what this bar means. This bar means such that x is a natural number between 7 and 14. So I could write this set as all the natural numbers between 7 and 14. It doesn't say including, it just says between. So I could say 8, 9, 10, 11, 12, and 13. So I can write all the elements in a finite set, or I can describe it using set builder notation. Now, set builder notation is really great when we have infinitely many elements, right? Like if I just said x such that x is a natural number, that set is infinite, right? It goes all the way from 1, goes on and on forever. So set builder notation is a nice way for us to write our sets using words. So here are the natural numbers written as sets. So my natural numbers are all the numbers that we use to count. right? Like I said, these are, also the counting numbers. Our whole numbers is the set of natural numbers plus 0. Maybe I should switch from blue so you can see this. It's the natural numbers and 0. The integers is the set of whole numbers plus all the negatives of the natural numbers. Those are called opposites or additive inverses. We'll get to that in a little bit. But integers are just positive and negative whole numbers. Rational numbers are any number that can be written as a fraction, right? But we can't divide by 0. And that set's infinite and hard to write. Like, how do you start writing out all the fractions? So we write it as P over Q, where P and Q are integers, right? And our denominator, Q, doesn't equal 0. The irrational numbers are any number that can't be written as a fraction. Those are going to be numbers like pi, square root of 2, e. If you push e on your calculator, it's an irrational number. And the way we write these in set notation is x, such that x is a real number. All these numbers are real, right? They occur in our everyday life. But it can't be represented by repeating or terminating decimal. And the real numbers include all of everything listed above, as long as x is a rational or irrational number. So here's how the number system's contained. We've got the natural numbers. You add 0, you get the whole numbers. You add the negative numbers, you get the integers. You add all the fractions, you get the rational numbers. Because remember, every whole number or integer can be written as a fraction over 1. Then you've got your rational numbers. And all of those together make up the real number system. So let's list all the elements in each of these sets. If I have x as a natural number less than 6, the natural numbers start with 1. So I've got 1, 2, 3, 4, 5. That's it, right? Because it's less than, not less than or equal to. This is a finite set. What if I said x is an integer greater than or equal to 4? So it has to be greater than or equal to 4. So 4 is included. 5, 6, 7, 8. Wait, the integers are infinite. They go on forever. So this is an example of an infinite, which I always misspell when I'm typing, set. And all those numbers and all those number families can be represented on this real number line, right? We've got 0, that's our origin. We kind of consider that our home base. We have our natural and whole numbers. We have our integers, our rational numbers, and our irrational numbers. And all of this makes up the real number line.